Can you see my slide?
Yes.
They scroll?
It looks good.
Okay.
Please proceed. Sorry, I was going to introduce you. So Andrea will be talking about short GRB simulations. Take it away.
Yes, hello everyone. My name is Andrea Pavan, and I am a PhD student at the Padova University. I would like to thank the organizers for inviting me to this very nice workshop. I'm going to present the paper that I recently published together with my supervisor, Dr. Riccardo Ciolfi, and in collaboration with Jacqueline Ani and Andrea Mignone, where I perform numerical simulations of short gamma reverse jets, which propagate through a post-merger environment that is directly imported from a binary neutron-star merger simulation. Short gamma rebursts are powerful astrophysical processes whose association with binary neutron-star mergers has been recently confirmed with the detection of the multi-messenger event GW170817, GRB170878. However, since there was a 2 seconds delay between the last gravitational wave signal and the first detection of the gamma ray burst during that event, we still don't know which was the nature of the central energy that powered the short gamma ray burst jet, and how it propagate through the surrounding environment, leading to observe prompt gamma ray emission. In order to investigate this, the main tool is represented by numerical simulations. In particular, the merging process between two neutron stars and the subsequent jet production are typically proved by means of general relativistic numerical simulations, which have shown, for instance, that there could be two main possible scenarios for the jet launch. One is the so-called black hole accretion disk, and the other is the magnetar scenario. The latter, in particular, has been recently investigated by my supervisor, showing that in the case a long-lived massive and magnetized neutron star remnant is formed after a binary neutron star merger, a powerful collimator relativistic outflow can be generated. However, its power is most likely insufficient to generate a typical short gamma ray burst jet. On the other hand, there are many works which indicate that a black hole accretion disk system is a place where a typical short gamma ray burst jet could be generated. The large-scale evolution of a jet after its injection is typically probed by means of spectral relativistic numerical simulations, which have shown, for instance, that in the case of GRB 170878, the observed light curves can be nicely reproduced considering an off-axis jet emission, where which was originated by the interaction between the jet with the surrounding merging environment. However, all of these simulations present several limitations. In particular, the binary neutron-star merger simulations are notoriously computationally expensive, and because of this, they can cover only very small space-time scale of the jet evolution. On the other hand, the spectral relativistic jet simulations at the large scales are typically performed separately from the binary neutron-star merger simulations and adopting handmade initial conditions for the remnant and the surrounding merging environment, which are inspired from the results of the binary neutron-star merger simulation, but they lack of a direct connection with any specific post-merger environment. In our paper, we provide a numerical procedure which is able to directly import data from a binary neutron-star merger simulation into a special relativistic code, in particular the Pluto code, in order to perform a jet simulation. In particular, we carried out a general relativistic hydrodynamical simulation of a binary neutron-star merger extended up to about 160 milliseconds after merger, which led to the formation of a massive neutron star surrounded by the merging environment. We firstly read all the data from this simulation using the post-cactus Python package by Wolfgang Castaun, mapping them firstly into a three-dimensional uniform Cartesian grid, where we set the resolution equal to the original resolution of the binary neutron-star merger simulation at 380 kilometers. And then we import this data into the Pluto code, adopting a three-dimensional spherical computational domain, where we excite the innermost radial regions up to 380 kilometers, by which the large-scale evolution of a short gamma ray burst jet is expected to be unaffected, and allowing us in such a way to properly reduce or even neglect the general relativistic effects during our special relativistic jet simulation. We also set the computational domain with a logarithmic spacing along the radial direction in order to maintain higher resolutions close to the excised region from which the merger outflow came out, and reducing the total number of grid points going to larger distances in order to reduce the total computational cost of the jet simulations. We perform a purely relativistic hydrodynamical jet simulations where we used the so-called Taube equation of state that allowed us to consistently treat both the ultra-relativistic jet and the sub-relativistic expanding merging outflow. We also took into account the Newtonian gravitational field from the central compact object, and we treated it consistently within the framework of the special relativity. And in order to perform the jet simulations, we adopt the paradigm in which the jet is powered by an accreting black hole system formed after the collapse of the massive neutron star remnant. However, since our binary star merger simulation didn't produce by itself a black hole disk system, we artificially model its formation, adopting appropriate radial boundary conditions at the inner radial boundary. In particular, we set by hand the time at which the neutron star should collapse. And in the case this time is said to be larger than what is covered by the binary star merger simulation itself, we perform a numerical extrapolation using a linear fit of the angle average fluid variables computed at the inner radial boundary of the spherical domain directly from the binary star merger simulation. We modeled the collapse of the neutron star using outflow or zero gradient boundary conditions at the inner radial boundary, allowing the material of the merger outflow also to fall inside into the excised region, and introducing an extra acceleration term which mimic the gradual space-time and angle-dependent decrease of the radial pressure gradients from the central compact object, as expected in a realistic formation process of a black hole disk system. And then we inject a top-hat jet with an initial opening angle of 10 degrees and an initial Lorentz factor equal to 3. And we set the two-side luminosity of the jet with an initial value of 3 times 10 to the 50 erg per second, and with an exponential time decrease where we set the time scale of the decrease equal to the accretion time scale of the accretion disk that surround the black hole that power our short gamma burst jet. Here you can see the results of one of our jet simulations where we set the collapse of the neutron star at 100 milliseconds after merger. And the simulation is extended up to about 1 second after merger. At that time, the jet reaches larger distances of the order of 100,000 kilometers. You can see that after the jet is injected, it breaks from the surrounding environment, forming the jet cocoon structure with a head that is able to reach a Lorentz factor of the order of 40. And you can also see that close to the base of the jet, the share between the jet and the surrounding material leads to several Kelvin-Helmholtz instabilities, which perturb the collimation shock at the base of the jet and produce several asymmetries on the jet structure at the large scales. Moreover, you can see also that due to the gravitational pull of the central compact object, there is an efficient accretion process toward the center, which favored the formation of such Kelvin-Helmholtz instabilities and allowed the jet to excavate more easily the surrounding environment, widening a lot its initial opening angle. In the plot on the right, on the left, you can see that there is one of these Kelvin-Helmholtz instabilities indicated in the upper plot, which we note during the jet evolution. Such instability leads to an intense barrel loading into the jet structure, and this perturbs the collimation shock at the base, and this is at the origin of the several asymmetries observed in the jet structure at the large scales. In particular, in the plot on the right, you can see several angular profiles at the large scales on two fundamental Cartesian planes, on the top of the radial average Lorentz factor and on the bottom of the isotropic equivalent energy. And you can see that there are asymmetries both within the same fundamental plane, but also between the two fundamental planes, indicating that there is a clear 3D asymmetry of the jet at the large scales. Then we studied more in detail the effect of the gravitational pull from the central compact object, performing the same jet simulation as before, but without including gravity. And we know that in the latter case, the jet reaches larger Lorentz factors, 2 times larger than the previous case. But also there are less Kelvin-Helmholtz instabilities close to the base of the jet, and so less intense and less frequent baryologic episodes inside the jet. And this allowed the jet to maintain an higher correlation through its evolution. And at the end of the simulation, the jet is less perturbed with a less turbulent structure at the large scales. We then investigate the impact of adopting handmade initial conditions for the merging environment at the time of the jet launch. And to do this, we perform the same jet simulation as before, but assuming an initial isotropic and homologous expanding environment at the time of the jet launch. And comparing the results between this jet simulation with the previous ones, we note that in the case of an initial spherical and homologous expanding environment, the jet needs to drill more matter in front of it in order to break from the environment. And this leads to a delayed breakout time of the jet. And due to the more isotropic initial environment, the jet is more symmetric at the large scales with a reduced Lorentz factors overall. And then we study also the dependence of the jet evolution on its launching time. And in particular, we perform a jet simulation where we set the collapse of the neutron star at 200 milliseconds after merger. At this time, at the time of the jet launch, there is a factor 3.6 more massive environment surrounding the injection site. And this leads to, again, to a delayed breakout time of the jet after its injection. And it allowed to maintain an higher collimation of the jet through its propagation. And at the end of the simulation, about 1 second after merger, we note an higher collimated and less expanded jet with a reduced Lorentz factor overall. So in conclusion, in our work, we have performed the first time numerical simulation of a short gamma reverse jet propagating through an environment that is directly imported from a binary neutron star merger simulation. And we observed that using simplified environments can change significantly the evolution of the jet, also at the large scales. And we also noted that it is important to include the gravitational pull from the central compact object during the jet evolution, because it plays a critical role on the jet dynamics and on its final fate. And eventually we have confirmed, as already seen in other works, that there is a strong dependence on the launching time in the jet evolution. And in the future works, we will also take into account the magnetic fields. In particular, we will directly import the magnetic fields of the environment from directly from binary star merger simulations. And we also test a more realistic prescription for the jet injection. So not more a simple top-hat jet, but for instance, a structured jet. And in order to increase the resolution of our 3D simulation, we are thinking also to use an adaptive mesh refinement algorithm for our jet simulations. And eventually, we are thinking also to include some radiative transport mechanism in our jet simulations. So that's all, and thanks for your attention.
Thank you. We have a little bit of time for a question. We have applause. Wolfgang, do you have a question?
Yeah, first of all, this looks very promising. I have a more technical question. So when you do this handoff between the fully general relativistic and special relativistic, what do you do about the equation of state? Because typically you have a different equation of state and which have maybe an overlapping range, but you definitely do not want to sort of change the temperature or something accidentally. So I guess these must somehow match. Or did you design some EOS that has an incredibly large density range? How does this work?
Yeah, we actually took into account this effect, and in particular in the
Hello, is it my connection or
No,
Andrea's?
I lost sound as well.
Okay.
yeah, can you hear me?
Yeah, we can hear you now.
No.
Okay. Yes, of course, the equation of state is different since in our Pluto simulation, we use the Taube equation of state and not the equation of state used during the binary storm merge simulation. And so in order to check if the results are consistent, we perform the following test. During the simulation that I showed you before, we directly import from the BNS simulation the pressure and the rest mass density, and of course the velocity, and we compute the internal energy density with the Taube equation of state during the Pluto evolution. And this is what I show you in the plot with the green line. Then we perform the same simulation, but where we import the rest mass density and a pressure that was directly computed using the Taube equation of state from the central energy density, from the internal energy density of the BNS simulation, and then we perform the same jet simulation. And eventually, what we obtained is that actually there is some differences between these two tests, but the differences are very, very smaller than, for instance, what we noted if we remove the gravitational pull from the central object. So it seems to be not a strong dynamical impact in our jet simulation, the change in the equation of state.
Okay, thank you. I think we have to move
Thank
to
you.
the next speaker.
Yes.